Okay, let's start. You ready? Okay, since we have many slides today, so I better start the lectures now. Okay, so let's start from the communication part. Okay, so today I just want you to understand about the signal and also data. So of course, this subject is about IoT. And I think because you all have background a lot in computer core subject, but not signal processing and also communication. So it's good to like give you understand also about the communication and also how data and signal can transmit from one device to another devices. Okay. So the objective of this handout is about let you understand data and signal. All right. So actually this slide is not mine. I just used the slide from the textbook list here from Dr. Fulo-san. This is very well-known textbook for data and networking. Okay, so I just used his slide for presentation and also add some slide for like adding you or make you more understand. Okay, so to be transmitted, data must be transformed to electromagnetic signal. But before I go further, I just want to ask about what can you like name the data you know, and what difference between digital data and analog data? Can any of you share? So what is the data and what difference between data and signal? And if I ask you to name one data, okay, say analog data, what type, what data are you thinking about? Any of you can share? Maybe if I ask you to name one analog data, what you want to name? Anurag, do you have microphone? I want to like have a class more active, man. So please help. Or any other student? Do you understand the word analog and digital? I think you have heard, right? And actually analog and digital, I mean, the data have two kinds of, we can classify the data in analog and digital, okay? And we also can classify signal in analog terms and digital terms also. Okay, so anyone wanna share or discuss? No? Okay. All right. Okay, let's see. The data can be, as I mentioned in the previous slide, data can be analog or digital. The term analog data refers to the information that is continuously. Okay, it is the information, say specifically, actually it is the user data or the data from the device in terms of IoT application. So if this information is continuous, we can say that that is analog data. And if we think about digital data, it refers to the information that has a discrete states, or in other words, it's not continuous. Okay, analog data takes on continuous value and digital data takes on discrete value. All right, for today's discussion, it will cover this topic, analog and digital data, analog and digital signals, and also you have to understand this word also, periodic and non-periodic. Then if you understand already, we can go further for like to understand the bandwidth that you have to prepare for transmission. Okay, you have to understand this first. Okay, let's see. analog and digital data. If I asked you before, right? If you want to think about analog data, according to the definition, analog data are continuous and take continuous value. So the example can be video or audio or streaming, right? Because we can get the value continuously, right? So video, audio as a good example for analog data. Okay, this is from the source, right? This information or say that the data is from the source. And how about the digital data? Digital data have discrete states, okay, and take discrete values. For example, text and integer, right? When we talk about text, it's like you can classify one by one alphabet, right? It's not continuous value, so we can classify that the text can be digital data. And integer also, the number is not continuous. I mean, the integer is like 1, 2, 3, 4 is discrete states, right? So the integer can be classified that it is the digital data. And how about signal? What's that? What is signal? Actually, if we have just the data and information cannot be transmitted to the medium. Okay, because we cannot like send the video and audio or even text and integer into the medium directly, but we have to convert this data to be we can say signal, or actually it's like electric signal. It's like when we talk about signal, you can imagine that we have like in y-axis can be voltage or ampere, or I mean current, right? This is a signal, or sometimes this current, right? It can be converted to be a power. Okay, so the data should be converted to be a signal. Then the signal can be transferred into the medium. But it depends on the medium. But for wireless communication, the signal like voltage in terms of voltage and ampere or power in watt cannot directly propagate into the air. I use the word propagate. Propagate means like, okay, it's like a wave to go into a medium. In this case, is wireless channel. So in that case, I mean, in wireless communication case, the signal have to be further converted into electromagnetic wave. But actually, you may say that the signal actually is the wave. But if we use a term of signal, it's a kind of a wave, but a low frequency. But if we use our electromagnetic wave, the most different part is that the wave, especially communicate in wireless communication, is a high frequency. So we have several steps to convert our information. Say from the sensor, you get some data, right? And then you have to convert that data to be a signals. And then let's see if the medium is a cable, you may directly send the signal into the cable. But if not, for example, it is a wireless channel, you have to convert again the signal to be a high frequency wave that is more suitable for wireless channel. So there's a kind of, basic step to convert or prepare your information to be suitable for communication. All right, so how about the signal? Then come back here. If we talk about analog signal, it is, we can use the term electromagnetic wave, but as I mentioned, the frequency will be low. Okay, so it's kind of like not more than the unit of kilohertz. Okay, so the wave or the signal, it continue. It is, the value is continuous or continuously varying according to time. Okay, And it depends on the frequency also. Here, actually, I already explained. It depends on the media, what frequency should be. It can be a low frequency if you use a media as a wide media. For example, you use copper, or you can use fiber optic cable, or you can use atmosphere or space to be a medium for accompany the signal to the other end. Okay, so in here is very important also, analog signals can propagate analog and digital data, especially in terms of wireless communication. Every type of data should be converted to be analog signal before let it communicate into the air. Okay, I will explain later this one, but I just want to say that, okay, for example, if you have like, say text, for example, I type this one, and you know, when you type this one in your keyboard, it should be converted into the terms that computer understand, right? You are a computer-based engineer, right? You understand well that computer understand everything in terms of bits, right? And the bit, I mean, basic bits, there are two basic bits, which is 0 and 1, right? So every alphabet and also integer should be converted into a set of bit, right? We can call that ASCII code, right? And then after that, after the computer understand this text already, and it will be some set of, I don't know, maybe some set of the binary 0 and 1. Computer understand this one, right? And this is a type of the digital data, right? And then what I'm going to mention is that when you propagate this one into the medium, this one will not be propagated directly, but it should be converted into the analog signal by accompany. I mean, there is a one signal accompany this information into the signal, okay? And that one, the wave that carry your data is called carrier signal. Okay, and this one, when it mix up together, this term is called modulation. And after that, it depends on the type of modulation. But anyway, after it mix up together, for example, if 0 comes, so the amplitude of the carrier change to be 0. But if 1 come into here as an input, then the amplitude can be like the same. And then when 0 come again, it become 0 and 1, like that. And 1 come, it become the same. So when this signal propagate into the air, the one who want to detect this data can see from this one that, okay, when you observe this one, actually this is called OOK signal. Okay, on-off keying signal, I will explain in the detail again about modulation technique, but I'm going to say that the things that propagate into the channel is this one, not this one. Okay, this is the data, but this is, it's not proper to propagate in the air anymore, because the medium don't understand, right? So the medium can accompany the high frequency wave, and then we can use the carrier frequency to bring this information in the air. And this one is analog signal, right? So the value change continuously. Even sometimes it flat, it means no data, and then come again continuously. You can have many value of amplitude of this one. Okay, so this one can be classified as analog signal. This is an example that the analog signal can propagate both analog and digital data. All right. Any question? If you have question, you can ask anytime. So how about digital signal? In other words, the digital signal is that a sequence of a voltage pulse that may be transmitted over, copper wire medium. So it depends on the medium, as I mentioned. If wireless channel, it should be analog signal, because the atmosphere or the air, like the wave that it have a high frequency. But for a copper wire medium, it can be accompany a low frequency, or it can be digital signal also. Do not need to convert the digital data to be a digital signal. But anyway, if you have the same data here, this textbook, this text, it convert to be binary or a set of bits, right? And then this one, if you want to send this information in a copper wire, it can be transmit also, but the part of modulation maybe not need. But anyway, this one have to convert to be a signal first, right? Because the cable don't understand this also. But the cable, if you learn from, network communication, what subjects that network information and security, Ajahn may talk a little bit about a medium. I'm not sure. A medium, I mean the wire medium, and then characteristic or property in wire medium include like something capacity or in induction and then resistor. So this one is a kind of electric circuit, right? So it can accompany the signal also in the medium. So what I mean is that whatever the type of data are, it can be digital data or analog data. But anyway, the first step you have to do is to convert the data to be a signal. So the terms of digital signal is that it is also, again, some kind of voltage or current, or you can convert to be a power also. So the digital signal can look like this, can be like, a sequence, right? The sequence of the pulse means as a rectangle pulse. So it can be like this. It depends on type. But anyway, the y-axis represent the signal. So this one can be, for example, 1, and this is -1. And the positive pulse can be represent 1, bit 1. And the negative pulse or negative value of voltage can be represented with 0. So in this case, you can, like, if you have the information of 1, 0, 0, 1, you can easily convert this data, digital data, into a digital signal like this. But if analog, it can be like maybe like this. And it more like not like change immediately, but the value varying according to the time that passed by. So again, I just want to say that every data have to be converted into the signal first, and the type of signal that should be converted depends on the medium. So this is the example of the analog signal and digital signal. For here, you can see that the value of the y-axis, say the voltage change continuously, right? It changes continuously. You cannot count the number of level of the voltage. It can be from -1 at this point and change a little bit. It can be like dot xxxx blah 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 until maybe this is 2 volt. And then if I ask you to count how many voltage level is this signal, you cannot count because it is the range from -1 to what? To 2, right? So the range can be the real number. So if you want to classify which one is analog signal and digital signal, you can count from the number of value also. Okay, for analog signal, you cannot count exactly number of the value in the range. You can say that it is an infinite number of the value in the range. But if you take a look in this picture, this is digital signal. And then if I ask you to count the number of value, you can just count the, the value of y-axis, right? And you can observe that there are 4 levels. Say this one, maybe 1, 2, and here 0, and here -1. So from this time period, okay, the amplitude will be 1. And then for this period, it will be 0 voltage. And from here to here, the period of time, you can see the level of 2 volt. So you see, you can count the number of value, and you can say that the value of this digital signal just 4 level, which is -1, 0, 1, 2. Okay, so this is a limited number of values. So you can say that this is the digital signal. Okay, again, if you think, if you talk about signal, it should be represented in voltage or current or power. And then there are two types to show the signal, how it looks like. So this type of graph called time domain. Okay, time domain means that you see the value of the signal with the time change. Okay, when time change, you can see that the power, what power is that in some period of time, right? Okay, so that is the digital analog data, digital analog signal. I think you can have an idea. Any question? So if no, let's continue to analog signal, but more specific in the terms of periodic. This is very important. This is not hard or difficult, but you have to understand at least characteristic of the periodic signal, because every signal in the world that generate in nature is not periodic, but we try to analyze it. As an engineer or a scientist, we have to analyze something, right? So we can analyze every signal in terms of periodic analog signal. So in this section, you have to understand the characteristic of periodic signal. Okay, please let me know if what I'm going to teach today is too simple. If you understand already, I will skip. All right, for data communication, we commonly use periodic analog signal and non-periodic digital signal. But for this topic, I will focus on periodic. Okay, periodic analog signal can be classified into 2 types. Okay, one is called simple. Okay, another one is called composite. A simple periodic analog signal is just a sine wave. So I try to use the color to represent the same thing. The simplest terms of periodic analog signal is sine wave. But actually, the composite signal can be combined with many sine wave also. And this is not simple, right? So we call this one composite. Okay. Okay. A composite periodic signal is just the combination or composed of multiple sine waves. Okay, this is the time domain concept. When I talk about time domain, it's a kind of function. You learn long time ago already about a function, right? say, so now we are talking about the signal. So I represent the S, the lowercase letter S represent the signal. And then if I want to consider the signal in time domain, so it should be this parameter, okay? S is a function of t. So if t or time change, the value of signal will change also. This is the time domain representation of the signal, okay? Analog signal, actually, the signal intensity, or intensity means like the y-axis, varies in a smooth fashion over a time. No break or discontinuity in the signal, right? But for digital signal, the signal intensity mainly a constant level for some period, as shown here, right? The intensity, or say the value of the voltage, for example, constant over some period of time, and then suddenly change to be 0 in this case, and then suddenly change again to be 2, like this. This is the representation of digital signal. All right. So in formula, to represent a periodic signal, it's like this. The word periodic means that the shape of the signal will be exactly same for the same period of time. Okay, so it can be analog or digital signal pattern that repeat over the time. So this is the representation of periodic signal. So we have ST, right? But then T change, continuously change, the time change, right? And then from T change to be T plus T, small t plus period of time T. Then you can see that that is the same value of S. Okay, time can be like from minus infinity second to infinity second. This is the representation. Even the time change, the signal will be the same. This is called the periodic signal. Okay, and then the big upper capital letter T here represent the period of the signal. So this is not the how to say, this is a constant value. Okay, this is not changed, but we have to like consider this value. So we mostly use the terms of a big alphabet to represent a constant value. So this one time, I mean the period of the signal in the unit of second represent by the big T. And how about the a periodic signal? Actually, a periodic can say non-periodic. Okay, so it's not like in other words of this term. Okay, analog or digital signal pattern that doesn't repeat over time, we call that signal as non-periodic signal. So this is the example of the periodic signal. Okay, this is sine wave, right? And then we mentioned that, okay, we want to observe this period T, okay? This period of time, especially in sine wave, one period means that there is time for completely half one cycle. So this, I think you all understand it. This is sine wave, right? So it starts from here, and then to complete one cycle, it stops here. So the time spent from the beginning and the end of the shape of the sine wave called the period. Okay, and then you can see that for this one, so if this is T, right? And then count again plus the period of time. So this one can be T plus T. And then you can observe that the signal will be the same pattern, right? So this is, of course, 100% periodic signal. And this is the simplest version of periodic signal. And then, of course, this is analog signal, right? Analog, I mean, periodic analog signal. And how this one? If you observe from the graph, you can say that this is not analog, but digital, right? And there are two levels of this signal, which is A and minus A. But this digital repeat the same shape also over some period of time, right? So if you think about this one is t and then plus again this t, the same duration of time, right? And then you can see easily that the shape of the signal is the same. So you can say that this is the digital periodic signal. Okay, so as mentioned, the simple periodic analog signal is a sine wave. So this one cannot be decomposed into simpler version of signal anymore because the sine wave is the the simplest version already. So it cannot be decomposed into another shape of signal anymore. Okay, let's take a look at a parameter of the periodic signal. So for sine wave, okay, let's see this general formula of the sine wave. Have you seen this before? Have you learned this before in physics? Let me know. If you see this equation, do you understand each parameter in this equation? If you already understand, I can go fast. Can have you seen this before? This equation. Are you?
Yes, I have seen that.
Okay, so you understand every parameter already, right?
Actually, yeah, I understand.
Okay,
Maybe.
so maybe if I imply that everyone understand also. Then let's see here. So if I ask you to write this graph in formula, do you think you can do it? So first of all, you have to understand this parameter first, right? 2 pi is the constant, f is the frequency, and this representation means the phase. So if you observe from this graph, and then you can put it in the formula, that is fine for me. So I can skip this one. Do you think you can do that? So for example here, okay, I zoom in. Okay, for the first graph, I try to hide the panel. Okay, so this one, as I mentioned, you have to understand at least 3 parameters. A is the amplitude. Okay, amplitude means biggest value in y-axis. So if this is voltage, so you just see the maximum value of it. So that is the amplitude. Actually, this one is the definition of the amplitude. The amplitude is the maximum value or the strength of the signal over time. So it can measure in volts. So in this case, you can easily see that the amplitude equal 1, right? And then how about this parameter f? F means the frequency. Okay, let's recap. What is the frequency if I ask? Okay, let's see from the figure. What frequency is this? Ping, are you there? Help me. What frequency of this graph? And what frequency of this graph? Is that same? Pink's not here. Okay, maybe brown. Brown, what frequency of this graph? No response? Okay, mine maybe. What frequency is this? No one here? All right. But you type your name in your chat box.
Is it 1 hertz?
1 hertz, I think.
Okay, how about this one then? This graph?
It's 2 hertz. Right?
2 hertz. Okay, how about this one?
Which one,ครับอาจารย์
This one,ค่ะ. This one. it mentioned here that is F is 1. It's 1 Hertz also,
Oh, okay.
right? And how about this one? This is 1 Hertz also. But then how can you know that what frequency are they? So what is the definition? The definition of the frequency is that how many cycle per second of the sine wave, right? So you just capture, take a look in 1 second, and then you count a number of sine, right? And then, yeah, actually the cycle per second can be named as hertz. That is the unit of frequency. So we can easily see from here that, okay, for 1 second here, you can count a number of cycle is 1. And 1 second here, you can count a number of cycle 2. So the frequency is 2. And for this one, for 1 second, you can count 1 cycle. So the frequency is 1 also. And then this one, the shape is not start from starting point of 0 degree, but you can count that from here, and then it lasts to here is 1 cycle also in 1 second. So you can count the number of sine wave 1 cycle in 1 second. So this one is 1 Hertz also, right? So it's easy. So you can represent frequency here as we discussed. How about this parameter? What does it mean? This one? This is the phase. Do you know the phase of the signal? Phase of the sine. Okay, let's talk about the definition first. The phase is to measure the position of the waveform at time equal to 0 second. Okay, within a single period of a signal. Okay, so simple says that when you want to find the phase of any signal, you just take a look. Okay, in time domain, you take a look here. T equals 0 second. And then let's see what shape is that. So if this the shape of the sine wave, okay, so at T equals 0 here, you can say that at this point, phase is 0. But actually, this signal or sine wave actually move all the time, right? So it can move. Okay, so let's change. Actually, the green signal move all the times, and then you capture the signal like this. So it moves, like for example, move like here or even this direction. But then anyway, then you capture to observe the signal, this second signal. So if I'm asking you to find a phase, what is that? Tang, you there? What is the phase?
90 degrees.
Yes, right. Why? Because you take a look at T equals 0 and then you capture that the shape is here, right? This is the position of 90 degree of sine wave, right? So everyone understand, I guess. So it changed again. It moved again, and then you capture that this is the sine wave that you want to observe the characteristic, or it arrived in your device with this shape. And then what's the phase is this? Maybe pi, right? Pi or 180 degree, right? So this is the how to represent the signal, okay? By to find each parameter, you can observe the amplitude and frequency and also the phase of the signal. And you can imagine that this sign actually is the wave. When it arrives to the device, the amplitude may change and the phase of course change for sure, because the shape of signal move all the time, right? It depends on what time that you want to see, I mean instant time that you want to observe the signal, the phase change. But you know, these three signal from three graph here actually is from the same sine wave. Okay, so you can represent the signal in this formula. Okay, so if you know amplitude, for example, this graph, you can say that A is equal to 1 voltage and F is 1 hertz and phase is 0 degree. You can represent here as the unit of radian. It can be 0 to 2 pi radian, or if you can represent the phase as the degree, it can be 0 to 360 degree. Okay, but anyway, you can represent in the formula here. Okay, the period equal to 1 second in this example, right? So you can represent this signal as st equal sine 2 pi t. Then if I just write this formula, you have to understand what amplitude is that, what frequency, right? What is the phase, right? So if I just write this equation, so the amplitude is not disappear, is there, but it's 1, right? 1 multiplied by everyone should be the same. Okay, so you have to imply, you have to like understand from the equations also. But this one is the parameter of frequency gone, but actually not gone, right? It represents 1 also. And the phase here not appear here. So you can imply that it becomes 0 phase like that. Okay, so I think you understand already. Okay, so let's see, to ask yourself, what are the 3 important characteristics of the periodic signal? Okay, so I repeat again that there are 3. One is amplitude, right? Another one is frequency, another one is phase. So you have to understand the characteristic of each sine wave. And then the second question, draw a sine wave in 1 second duration with A equal 2 and the period equal 0.1 second and phase is 190 degree. So what the shape of signal is this? So this one is the key point. I mean, to draw the graph, you have to know that what the duration of time you have to repeat the same shape of the signal, right? So it mentioned that for 1 cycle of sine wave is spent only 0.1 second. So in 1 second here, if you want to draw the graph in 1 second, so how many cycles are there? So since, 10. Yeah, sure, right. So 10, right? So for 1 cycle, you spend 0.1 second, right? So in 1 second, you have to have like 10. Okay, this is not 10, but you understand, right? So you can count the number of cycles to be 10 in 1 second. And A here represent 2 volt. You have to represent here as a voltage. Oh, but this is wrong because it mentioned that the phase should be 190 degree, but for my graph, it is the phase of 0 degree. This is wrong for this question. So I'm changing to have a phase 190. It should be what? It should be like this, right? So it starts at 180 degree, right? And you draw again until 10 cycle. Okay, so you can get the sine wave with this characteristic. Right? So if I ask you, what is the frequency of this one? What's the answer? What's the frequency?
It's 10 hertz.
10 hertz? Yes, because if you just see from the drawing, in 1 second, you can count 10 cycles in 1 second, right? So it's easy to count 10 hertz. And then you can observe from the relationship also about frequency and period of time. Period of time and frequency is inversely proportional to each other. So if you know frequency, you can calculate the period of time in the unit of second. Or in this case, you know the period of time and then you want to calculate frequency. So you can say that, okay, this is 1 over 0.1, then the frequency becomes 10. Okay, so this is the simple formula to find the period of time and frequency also in periodic signal formula. Okay. All right, how about wavelength? Wavelength. What is the wavelength of the sine wave, of the sine? Actually, the wavelength and one cycle, I mean, let's say, when we talk about wavelength, we measure one period, one pattern of sine wave, one cycle of sine wave in unit of meter. So say the wavelength is to measure the distance. For example, if I draw this side, right? And then I want to find the wavelength. Okay, the wavelength is that you calculate the distance from here to here. The distance from here to here, say this one. So in terms of meter. Okay. But if you calculate it like the period, this can be the unit of second. So the shape of the signal is the same, but it depends on what part that you want to consider. And then it relates to the frequency also. If you want to calculate wavelength, from physics long time ago, you'll have learned this one, right? V equal F lambda. F is the frequency as we just discussed, and then wavelength you understand already, right? And then actually is the multiplication of frequency of wavelength equal the velocity of light, which is the constant. This is 3 times 10 over 8 meters per second. So I'm going to say that if you know the frequency, you can easily find the wavelength because this is constant. This is helpful for you in the future, maybe. If you are an engineer working with the operator, say AS through DTAC, and then you are thinking about applying the frequency that you have, I mean the company have, to different areas. For example, if you want to use the frequency in a low, I mean the small area, the frequency can be what? So if the small area, the wavelength can be short, right? So it's like this. So if you want to think about what frequency range should be assigned for each area, so you can like consider from here. Right. So if a small area, this is small, right? So the frequency can be very, very high. For example, if you want to install a base station in Bangkok again, and specifically in HM building, like you have a small tower inside a building, and the building is very small, right? So the distance, we can refer the distance as the lambda or the wavelength. So if it's small, then the frequency should be high, right? So you may observe often that when the operator assigns a frequency used in the area. For example, in Bangkok, 45G, maybe it allocates a high frequency range in a small area, such as, for example, in Bangkok, I mean the coverage area. But if you want to install a base station in very rural area, okay, say from one base station, and then, you know, rural area means that there's a small number of population there, right? And there's no need to like duplicate the base station to transmit the signal because it costs a lot to implement one base station. Then for rural area, and then you want to make a large coverage, say you can represent here as a distance. So you may think about that, okay, the frequency can be lower because the range or the coverage distance is long, right? So the frequency can be low. So for example, it can be used at like, I'm not sure exactly, but this is just for example for your idea. Maybe if you compare the allocate bandwidth from operator. It ranges from 700 megahertz until something like, I'm not sure exactly, but the unit of gigahertz. For example, say for 3G, I go back, but because I remember exactly the frequency. So for 2 gigahertz and 700 megahertz. So for the rural area, you can like use this bandwidth, I mean lower frequency band for a long distance, like in the rural area. But in a small area, when you want to apply one base station in a small area, it's better to use like higher frequency that you have, like that. So this is like how to apply what you have learned long times ago with the real scenario. Okay, so that's just what I want you to have imagination of the application. Okay, so all right, this one is just explain. This is just to show that the frequency is the same, the phase is the same, but amplitudes are different. Like that. Okay, and this I mentioned already, right? The relationship between frequency and period of time. And okay, let's go faster with this one. Okay, if I show you the figure and then you have to recognize what is A, F, V, right? And then in terms of like analyze the signal, you have to do it as the formula. So after you know this one, you can put it in the formula and then you further calculate it later on. Okay, I'm sure that you understand this one. And this is just the table convert between the frequency and the period. Okay, you can take a look by yourself. And this very simple question. So I skip this one. So this is just try to help you understand how to calculate frequency if you know the period of time. All right. Okay. So, okay, let's repeat again here about the definition of frequency. Frequency is the rate of change with respect to time. If it changes in a short span of time, it means high frequency, right? So like this, short span, right? But if it changes over a long span, so for one cycle, you spend longer time. So when you take a look in 1 second, the same period of time of 1 second, you can say that this is lower frequency and this is higher frequency. You see, when you apply it in real scenario, for example, you use Wi-Fi, the operating frequency you use is 2.4 gigahertz. In time domain, you cannot see like this shape for sure, because in 1 second, you have to count the number of 2.4 gigacycle, right? So you cannot like distinguish this by your eye for sure. So actually there are another type of the graph represent the frequency and the amplitude. We call that frequency domain. Okay, it's a frequency domain. Actually, the same signal can represent into 2 domains. What I'm drawing here is the time domain. You see, x-axis is time, right? And compare the time with the amplitude, and you can see the shape, how it changes according to time, okay? But for frequency domain, what you can see from the graph is that you just see what frequency is that signal and what amplitude is that. For example, here, okay, I give this 5 volt. The maximum voltage is 5, right? And I assume this one F is equal to 10, and this one F equal to maybe 2 hertz. Okay, for time domain, you can draw a cycle. 10 cycle per 1 second, you represent 10 hertz. But for frequency domain, you can draw this one. 10 hertz is just, okay, frequency is 10. because the unit, I mean the x-axis is frequency already, right? And the voltage is represented by 5. So this one, and this one is just the different representation in different domains. One is time domain and one is frequency domain, but this one is just to represent the same signal. Okay, so in this case, the signal have 10 hertz of frequency and have 5 volt of amplitude, like that. So this one is called frequency domain. Okay, in like you may see after this that we use frequency domain often because it's very difficult to represent time domain in very high frequency. Let's see, for example, Wi-Fi use 254, we cannot represent this one, right? But instead we just say that, okay, in our system there are the Wi-Fi which is work or operate in 254 gigahertz, or in this area we have also 5G, okay, 5G signal here, and 5G signal use 700 megahertz, and we can detect the power. Actually, it's represent power in most scenario, I mean in wireless communication. So if, for example, it can be like, if it converts to a voltage, it can be 1 volt, like that. So I'm going to say that we prefer to use frequency domain than just represent the time domain in case that we work with the real scenario which have a high frequency, right? Okay, so by seeing this note, if a signal does not change at all, what does it mean? Does not change at all, for example, you use battery AA, okay, and it voltage represent 5 volt, and it 5 volt all the time. So if I ask you what frequency is this, you cannot count, right? You cannot count the number of cycle in 1 second. So you can say that if signal does not change at all, the frequency becomes 0. Or in other words, okay, the second sentence mentioned that if the signal change instantaneously, say this is time domain and this is voltage or power, then the signal just like sleep, I mean say 0 voltage and then suddenly have peak, and like this. What frequency is this? So we cannot represent again the number of cycle. In this case, okay, the signal change instantaneously. The frequency is infinite. We cannot count the number of frequency. Okay, for the phase, I already explained. I skipped this one. And this is what I just explained, okay? One same signal can represent into 2 domains. This is time, this is frequency, you see? So this is sine wave, and you can count the number of 6. So the frequency is 6 hertz, and the amplitude is 5, and you can see the phase equal to 0. But if you represent this signal in frequency domain, what you can represent is just the amplitude and the frequency. And this frequency is 6, right? And the amplitude is 5. So the block, the height of this bar is 5 volt. So it's like that. This is frequency domain. Okay. All right. So how about this one? If we observe 3 signals at the same time, like this, we have 3 signal, blue, pink, and green. And then this is time domain representation. And then you can draw it in the frequency domain, right? So for example, if we draw the blue one, which is 15 of amplitude, I don't know the unit of it, but okay, let's say the integer value of the amplitude, then the frequency is 0, it's constant, no change. So the frequency is 0, okay? And the amplitude is 15. And then how about the pink one? The amplitude is 10, right? The number of cycles you can count, it is 8 cycles in 1 second. So move to a frequency of 8, then you can have the frequency of, the amplitude of 10. And then the last one is the green signal, and the amplitude is 5, right? The amplitude is 5, the height is 5, and then the frequency is 16. Okay, so this is a representation of the same signal in time domain and frequency domain. Okay, so what I explained is more on a single frequency sine wave, right? A single means one frequency. We consider only one sine wave, and we consider only one single frequency. And this one is not useful in data communication because you cannot find the signal in nature would have a very beautiful sine wave. Okay, but we have to understand this characteristic because we can use the math called Fourier transform. I'm not sure whether you learned this one. Fourier series and Fourier transform. Have you heard this before? This is the reason why you have to learn like a mathematics of Fourier series and transform, because if you are an engineer and work with the signal, you have to understand time domain and frequency domain, and you have to analyze every signal in the world by represent that signal in terms of the series of sine wave. Okay, can anyone of you let me know if you know this before or you have heard this before? Fourier series or Fourier transform? No
Not
one.
quite sure about that.
Not quite sure means you may heard, but you have not learned that, maybe?
Yes.
Okay, good, thank you. Okay, so this is not useful. I mean, just a single sine wave with one frequency. That signal never happen in real scenario. So we need to send a composite signal. Okay, what is that? A composite signal is a signal that made of many simple sine waves. So the composite signal is just the combination of multiple versions of sine wave with different amplitude and phase and frequency also. And this is the combination, and we can call this, we represent the signal as a Fourier series, okay? Series means that to consider it like the combination of every terms together. Okay, for every signal in the world, we can analyze based on this concept. We can consider the complex signal to be like more simple or simpler one by just consider, okay, any signal can be considered as the summation of the sine wave. And you understand well already, right? Everyone can answer me if I ask you understand frequency, amplitude, and phase. If you say yes, you just like combine it together. And the shape, of course, because it's a summation, is sum up together, right? So the output of the summation will be not sine wave anymore, but is another shape of signal. But if you look inside, or you can say decompose, okay? Decompose means that you extract each sine wave, then you can know characteristic of the output one. For example, maybe it's better to say, okay, I'll draw here. For example, you receive this signal, very fluctuate one, okay, change a lot, even a short period of time. And of course, it's not periodic at all. This is the real world signal. And then it's difficult to define this signal as a formula because it's not simple one, is not general term, right? So you have to analyze that based on mathematics you have known before, and one that you can use is the Fourier series, okay? And we can use, as I mentioned, Fourier analysis. So what the points are, for example, if I draw here as it can represent A1 sine 2 pi F1 t plus phase 1 and A2 sine 2 pi F2t with phase 2 and blah, blah, blah until in terms of sine, okay? So 2 pi Fn t plus Vn. Then you can represent this one as like this one, okay? Just a combination of multiple sine wave term. You may curious that how can we get this one, right? There's another story. Actually, if I teach you in like a subject of signal analysis or more in wireless communication, I will give some time to explain this one because it's very important for the one who want to analyze the signal. But for this course, I think I just explain the concept. You can get this one from things we call Fourier series. And there's a kind of like mathematic terms. I can show you the formula here. Okay. Just for your information, don't panic to see the integral again. Okay, for Fourier series, it's like this. This is the mathematic. Okay, so every signal in the world, we can represent with this one. And for the right-hand side here, you can obtain each, we call A0, AN, BN as the Fourier coefficient. And you can get this value from this integration. So you have to know the period, okay? And you have to know some information of the signal you want to convert. And then you do the integral, and then you can get the value of A0. And also for AN, BN, the signal information you have known multiplied by cost function, and then do the integral again, you can get AN here. And for BN, okay, so you have some information of signal and then multiply sine function and then do the integral, you can get BN here. And then finally, you can get this Fourier series, okay? And this is example, okay? This is the signal that I want you to represent in Fourier series. Okay, so you can get A0, AN, and BN based on this equation. And for this example, it's due for you already. So for A0, the value becomes 0, AN, it becomes like this. It becomes 4A divided by N pi if N is odd number, and become this value if N is, sorry, this is 159. And this is for N3711. So it depends on the integers here. So the integer here is the terms that you want to represent, the number of terms that you want to represent. For example, if you want to see the first term of sine, so N is just the index of the first term. Okay. And then for the first term here, for example, here, for example, if you want to find the term of A1, you go back here a little bit. So you want to find A1 terms, right? A1 multiplied by sine 2 pi N equal to 1, right? And F T. So you can represent A1 from what you did. I mean, from this example, it mentioned that for 1, you can get A1 equal 4A divided by 1 multiplied by pi. Okay, so you got N, oh sorry, you got A1, and then you put A1 in the equation here. See? 4A pi. This is A1, right? And in this term, it becomes like a cost function. Okay. So it represents here as a cos. It can be sine or cos. Cos 2 pi N equal to 1 ft. So this is the first term. right? For the second term, no for second term, okay? So it means that A2 becomes 0, 0 multiplied by A cos of psi becomes 0. And then let's see if it A3 is here, right? N equal to 3, then A3 become minus here, right? Minus 4A divided by N equal to 3, right? You insert N by 3. Then you put here as A3. And this is 2 pi NFT, so N become 3. And you do like this, like multiple terms until etc. Right? So this is a time domain that is like not only represent this one in terms of another formula, but you want to use Fourier series to represent this rectangle in the combination of sine or cosine waveform. You can use Fourier series as I mentioned. Why we need to do that? You know, this is quite simple, but just want to show you that the square wave can represent into the combination of sine or cosine together by using the Fourier series. Then another signal also can be represented in the same pattern also. Why we have to do like this is quite, maybe you feel like we have to integrate many things to get the summation of sine term. But after you do that, it's very simple, right? You understand characteristic of sine. And of course, even you have to do the integral, but to integral sine and cosine is quite easy compared to do other integral. So that is a concept to use Fourier series to represent every signal or every function that you want to represent from time domain to be like in this form. Okay, so this one is just, we call that the Fourier series representation of this rectangular wave. And then you can convert this one. I mean, if you want to just consider the frequency, you don't want to see the shape of the signal. Because, you know, this one, when you combine it together, the shape of the signal almost the same as the rectangle, but you want to see what frequency is in this signal. It's not only one frequency anymore, right? Because in this signal, which is rectangular one, represented by ST, represented by multiple terms of sine. And every terms of sine have its own frequency. So it means that actually this signal contains many frequencies inside. So if you just want to see the bandwidth or what frequency are in this rectangular waveform, you can represent it, just use the frequency domain. Okay, this is frequency domain, and then you can like, okay, draw a bar graph like this. We can say that even you don't know what exactly frequency is, but you can like represent it in the general factor like F. If frequency is F, then the amplitude is here, right? The amplitude is just the coefficient in front of the sine or cosine wave, right? So this is the amplitude A1 at frequency F. And for second F, the second harmonic is gone because 0 amplitude, right? So you cannot see because it's not there. The second frequency is not there. So you can see the third harmonic means when you multiply the frequency T times of the fundamental frequency, say F, then you can see the amplitude here, A3. But you see, this is the minus sign, right? So this is the negative value of the power or the amplitude. So you have to draw a graph like below 0, okay? Because this is negative value. And then for the fourth, there are no 4 terms, and then you skip to the 5th term, which is we call 5th harmonic. And then you see that the amplitude is 4a by pi. Okay, 4a divided 5 pi, and then so on. Then you can see that even very, it looks very simple rectangular wave, but you see, it contains many frequency. So what I mean is that when you want to transmit this digital signal, rectangular waveform in the medium, the bandwidth that you have to prepare is infinite. The bandwidth you have to prepare is infinite. Because of what? Because this signal consists of many frequency. It discrete frequency, but the range is from very low frequency until etc. Okay, then the bandwidth that you need to transmit this digital signal is not occur in the real world. So what I mean is that actually rectangular wave here represent the digital signal, right? Okay, digital signal is only two value of the level A and minus A. And if you want to transmit this one, you need to prepare a big bandwidth. That is not practical anymore in the real scenario. So what I'm going to say is that in the real case, you can just cut some information of this curve. Okay, so if you sum up to multiple, infinite term, many terms, and then sum up together, the shape will be very exactly same as the rectangular one. But if you want just to save the bandwidth, by the way, do you know the definition of bandwidth? What is the bandwidth, Ka? The bandwidth is the frequency the frequency spectrum that you have to prepare for data transmission. Okay, for example, in 4G, actually 4G used from 5 megahertz bandwidth until 20 megahertz bandwidth. What I mean is that if you want to transmit digital signal in 4G, it's not possible because what you need is infinite bandwidth. But for 4G, the lowest bandwidth is 5 megahertz, whatever the starting frequency and the end frequency is. But the maximum frequency subtract from the minimum frequency, we call this bandwidth. Bandwidth means the maximum F max minus F min. And yeah, in real scenario, it's not that much. Or even it much, like 20 megahertz for 4G, it's not like reserved for only one signal for infinite bandwidth, right? So what I mean is that the signal have to like distort a little bit to save the bandwidth for transmission. How to do that? So if you observe from this one, you do not use to spend like very large bandwidth, but you observe that after 7 harmonic, 7F, the amplitude is low, is very low, right? And the more term, the amplitude is lower, even there's exists, but the amplitude is low. So it not need to cover that part, right? What I mean is that for the real scenario, you just capture just, okay, this is the full representation and you represent it just like from here to here. Of course, by summation, only 3 terms and infinite term are different. Okay, for 3 terms, the signal may be, the shape may be like, not like that exactly same as the rectangular wave, but maybe there are some distortion, right? Some ripple, a little bit distort from the pink one. But you still recognize that, oh, this is a positive value of voltage, right? This part, and this one is negative value. Then you still recognize that, okay, this is bit 1, this is bit 0. You still recognize that. So even the shape of the signal is the most perfect one, but whenever you still detect it, it's okay. Okay, so it means that you just delete some other part that the amplitude is very low to save the bandwidth. So in this case, you do not need to spend bandwidth until infinite hertz, right? But you spend just this frequency to this frequency. So in this case, the bandwidth to send this information of 3 terms here equal 5f multiplied by f, subtract by f, so it becomes 4f. So it depends on what is the f here, but at least it's limited bandwidth. So it's reasonable to send this signal into the limited bandwidth. Okay, so this is very important. I know that to represent the sine wave characteristic is not that difficult for you, but for further analyze the signal, for example, use Fourier series, you have to understand like characteristic of periodic signal first. Okay, so any question so far? What I mean, okay, go back. We come far from the current slides. Okay, we are here, right? So we are at the composite signal and periodic, okay? Okay, again, recap a little bit. The composite signal is just the combination. Okay, let's see here. It's a combination of a simple sine wave with different frequency, amplitude, and phase. And then we can represent every signal by using Fourier series equation, okay? And then composite signal can be periodic or non-periodic. What I mean is that after you sum up the sine wave together, the output may be periodic or non-periodic, okay? But if the sine wave is periodic, for example, the example that I just showed for Fourier series, this one, actually this one is a combination of many sine wave, right? And it represents in rectangular wave. This one can say that this is a composite signal, which is periodic one because the rectangular wave is repeated, right, for the period of time. In this case, if the composite signal is periodic, okay, when you decompose it, you can get a series of signal with discrete frequency. This is what I just explained. Discrete frequency means that you can distinguish each frequency apart from frequency. Very clear. What I mean is that, okay, the one I show you is good example. I show again here. This one. This one, I didn't say that. Okay, anyway. So this one is example of this is called composite. Because it's a combination of the sine wave and then become exactly a rectangular wave, right? And the shape is periodic. So this is periodic composite wave or signal. And in this case, when you decompose it, okay, decompose it means that you extract each term of sine. And when you take a look in frequency domain, you can get exactly, discrete frequency from each other. Okay, we can call this discrete frequency detectable. And then go back here. All right. How about another one? So if the composite is not periodic, okay, you can decompose it, but you cannot get the discrete frequency, but you can get continuous frequency. I will show you next slide. And this is the example of the periodic composite signal, okay? It is a composite signal which is finally the output is the periodic one with frequency F. This type of signal is not typical in data communication. It's not happen, but this is like easier to start from this one, periodic composite signal. Okay, so we can consider it to be 3 alarm system, alarm clock, like, and then with different frequency. The analysis of this signal can give us a good understanding of how the composite signal is. So what it means from this one, okay, let's say that we have this red signal actually is a combination of these 3 signal, which is frequency of F, 3F, 9F, and then for every single of time, you see, you sum up each other, and then finally it become like this one. So it's very, how to say, look like the rectangular wave, right? But it still have some ripple, as I showed you in previous slide. Okay, so you can use Fourier series, and then if you use more term, this can be more flat. A ripple become flat, and then it become more like a rectangular wave. But anyway, for this example, it just want to show you that by adding just only 3 signal with this frequency and different amplitude, even the same phase, you can get finally this signal, the red one. And then after that, you want to decompose it. But after you decompose it, you can see that in time, this should be frequency domain. Please change it. So this is frequency. So you can see from the frequency domain that for the signal with frequency F have a highest amplitude, which is the amplitude of the pink one here, say A1. And then the second signal is the blue one, have the frequency of 3F, and the amplitude is A2 here. And then the last one is the black one with the frequency of 9F, and the amplitude is A3. So this is so you can see very clear frequency consists of this composite signal. But for another example, this is non-periodic composite signal. This is more general in the real world signal. This created by the microphone or telephone set when you when a word or two word is pronounced. Okay, in this case, the composite signal cannot be periodic. We cannot speak the same word with the same tone every time, right? Even I speak like 1, 1, 1, the tone is different. So the tone means the frequency. So the signal is not exactly same, right? So it's not periodic anymore. Then anyway, we can consider this as the composite signal. But after you decompose it, of course, we can decompose it and we can find that we can observe the frequency from 0 to 4 gigahertz, 4K hertz. You may confuse that how to get this one. There's a kind of mathematics to help you to convert time domain to frequency domain also. This is Fourier transform pair. But anyway, to represent here with non-periodic composite signal, when you decompose it, and then you take a look in frequency domain, you cannot see exactly what frequency are there, but more, you can see that the frequency are like continuous value of the frequency. Okay, so it range like, because of the tone, the amplitude of the tone change according to our voice. You can observe from here that the bandwidth of this signal is 4K hertz, which is the maximum bandwidth of our human voice or audio. Okay, it starting from 0 and maximum is 4K hertz, and we cannot like see from like a bar graph like this. Okay, but more we can see that the frequency are a lot because it combines from many sine wave with many frequency. Okay, this is the concept of the composite signal with periodic and non-periodic. Okay, this is another example. Maybe you can get the signal with the same bandwidth. I assume that you understand the word bandwidth already, huh? Bandwidth is can be calculated from the maximum frequency minus minimum frequency, right? So these two figures have the same bandwidth, right? The maximum is 5,000 and the minimum is 1,000. And the bandwidth to transmit this signal and this signal are same. But in detail, maybe it's not that important much because when we want to transfer signal, the bandwidth is more important. But anyway, I just want to show you that for non-periodic signal, we cannot see like discrete frequency inside, but at least we can see the minimum and maximum and we can calculate the bandwidth. And for figure A is the bandwidth of a periodic signal. So we can see, of course, minimum value of frequency and maximum frequency. And also we can see each frequency. Okay, we can distinguish from one from others. We can see it more clearly. Okay, this is just the characteristic of the composite periodic signal and composite non-periodic signal. All right, this is the example. I think you can take a look by yourself. Okay, just calculate the bandwidth. If you know that this periodic signal is decomposed into 5 sine waves with this 5 frequency, and it asks you to find the bandwidth. So you can just subtract from 900 to 100, and then you can get the bandwidth. Okay. And this is actually to draw as spectrum. I mean, spectrum is to draw a signal in frequency domain. It's given here that the amplitude of the signal is same as 10 voltage. Okay, so for this signal at frequency 100 have 10 volt and so on. Okay, frequency of 10 have 100 have 10 volt, 300 hertz have 10 volt also. So you can represent a graph of the signal in frequency domain like this. Okay, so this is just another example. I think it's quite similar. You can take a look by yourself. I think I spent too much time for this one. All right, so this is a real scenario example. For non-periodic composite signal is the signal propagated by AM and FM radio station. Even nowadays, your generation may not listen music from radio broadcasting station, but anyway, this is just like to give you an idea that for every station, when you drive a car and then you turn on your radio broadcasting, the AM will range from 530 until this value, right? Khertz. And then each radio station have 10 kHz bandwidth. So the music or the voice from DJ have to be converted into 10 kHz bandwidth. But you know, it depends on, okay, even the voice of a human, okay, it can put in every 10 kHz because the bandwidth of the human voice is just 0 to 4, or to say the bandwidth is 4 kHz. Then it's okay to transmit the voice of human and also the song in each station. Okay, we don't need to understand what frequency inside exactly, but anyway, we just consider bandwidth. It fit to the available transmit bandwidth or not. If our information have a bandwidth less than the bandwidth of the transmission channel, that's fine. Okay, similar to FM. FM range from 88 to 108 megahertz, and the bandwidth is bigger. There's some reason of a bigger bandwidth. So transmit by bigger bandwidth is better, right? You may observe that. For example, if you want to upload, or supposed to say download movie, the movie is a big file, right? And then if you have just very small bandwidth, it takes long times, right? But if you have a wider bandwidth, like, I don't know, maybe more than 5 or 10 megahertz bandwidth, so it can download faster, much faster. So this is a concept to have, like, to understand the composite signal, what bandwidth is it? And that bandwidth is smaller than the transmission bandwidth or not. If it is so it means that our information data that convert to be composite signal can be sent to that channel. Okay, like that. All right, this is an example. So you can take a look by yourself. And this is what I just explained before. We can use Fourier analysis as a tool that changes time domain signal to frequency domain. Okay. If a simple signal as a sine wave, you can easily draw, right? Okay, this is only one frequency. But if like very complex and fluctuated, how can we convert this time domain to frequency domain? We can, this recommend you to do the Fourier analysis. It can convert time domain here into frequency domain. Okay, I will not touch about the mathematics, but this is just the idea. All right. And this one is just want to talk about the harmonic. Okay, the harmonic is like when for a signal which have the smallest frequency, say F, like here. This is smallest frequency. We call this smallest frequency as fundamental frequency, represented by F. And then if we consider 2 times of fundamental frequency in terms of frequency, I mean, this is F, and then we consider the 2 times of cycle of fundamental frequency. This is called second harmonic. Okay, everything same. For this example, this second harmonic. For the third harmonic means that you have the 3 times frequency of fundamental frequency, right? So you have 1 cycle of fundamental frequency here. Then the third harmonic means that you have 3 cycles, multiply from the fundamental, and then in the same manner. Fourth harmonic means that there is a signal that have 4 times of frequency of fundamental frequency. Okay, so actually, if you, of course, every signal may not have the same frequency, but it can combine to each other, right? As I mentioned, when we consider Fourier series, we kind of consider the ST in terms of many sine wave, right? And for the first term, mainly it will be fundamental frequency. And the second term, it should be the second harmonic. Or we can observe from the frequency that there is a 2 times frequency, 2 times fundamental frequency, and the third term, and so on. So this can be combined together to have 1 output. Okay. Okay, as mentioned earlier, every composite periodic signal can be represented as a series of sine cosine function. And square wave can be represented according to the whatever integration we do in this one. And then we found that a square wave or rectangular wave can be represented with a series of odd harmonic of the sine wave. So when you calculate, for example, the second term, A2, it becomes 0. A4, it becomes 0. And if no amplitude, so it means that there's no signal for second and fourth harmonic, right? And even harmonics of the sine wave. So by proving from this set of the formula, we found that by represent the square wave, okay, it can be represented as a series of odd harmonic of sine wave. So of course, the fundamental sine wave is the smallest frequency represent the square wave. So see, this is one period of time, right? So fundamental means that only one cycle. And the third harmonic means that there are 3 cycles, right? And the fifth harmonic is the yellow one. There are 5 cycles. And then fundamental sine wave, third harmonic, and fifth harmonic sum up together is not exactly the same as the square wave, but it can be like something like this. There's some distortion. It's not like sharp 90 degree here, and amplitude is not flat. It's not beautiful as the square wave, but at least to represent the square wave as a digital signal is okay already. Because digital signal, we just define positive and negative value, right? Then most of the digital signal represent by the square wave, or you can say pulse, right? And that square wave and pulse can be represented by a set of sine, which is an odd harmonic of sine wave. Okay, that's maybe all. And this is just example to show that this is a sawtooth function. And then you can represent a cut of sawtooth here with a combination of sine wave. So ST here is like the estimation by using the combination of sine wave to represent the sawtooth signal. And then you can get A0, AN, BN from the integration here. Okay, and then after you get this equation, you can convert into frequency domain easily. Okay, you can see this is fundamental frequency, and this is amplitude of the fundamental sine wave. And this is the second harmonic, 2F, right? And this is the amplitude of the second harmonic, which is the negative value of the voltage, and so on. All right, this is what I just want to explain that, okay, to conclude. Every signal in the world can be represented with the Fourier series. And the reason why we need the Fourier series that we can observe easily here that it composed of sine wave, right? And sine wave, everyone know that sine wave have these 3 characteristics. A is the amplitude, right? 2 pi f is the frequency, and vary with t plus the phase. So if you understand this well and put this one together many terms with the harmonic frequency and with the different amplitude and phase, so that you can estimate more complex signal, okay, for signal processing. Okay, I think I will stop this slide here. Any question? I spent too much time. Okay, no question. Good. You sure? No question? I'm thinking if you can use Python to like find the Fourier series and analyze this. Let me see. That will help you like understand what I'm talking today. Okay, so if no question, I will take a break 5 minutes and then come back again for Bluetooth. You still here, right? Do you think you okay to continue for the second handout? Or you just want to make it next time? What do you think? No idea? If no idea, I will teach. So if you like feel like it's too much for today, it's good also to start again next time. Next time,ครับ someone say next time ครับ okay because the Bluetooth have many slides also I think it's better นะคะ to start